Okay, so we continue with glass where we stopped last class, right, and that is what we said, that when we look at the transmission coefficient over the solar spectrum, then what we see is it has got actually high absorptivity within the visible range, right. And then this is the heat radiation, infrared radiation, this is heat, and this is 6 millimeter normal glass, this is 6 millimeter normal glass. But if you have an heat absorbing glass, then this gets reduced somewhat, but this is significantly reduced, right. And net effect, of course, we see in solar gain factor, which you shall see in a moment. If you have gold coated glass, then overall transmission, transmittance reduces, but of course infrared radiation significant reduction would be there. Beyond this, this is infrared region. Nickel coated is somewhere here. So, by coating you can reduce down the heat absorption, right. Visible light, some reduction, some places it would be there. Photochromatic glasses, they are usually with bromides there. So, what happens is they are sensitive, their transmittivity or transmission coefficient depends upon the amount of light falling in. So, that is a function of, so that is kind of an intelligent sort of a thing. So, if there is too much of light, it will not allow, if there is less light, it will allow. So, photochromatic glasses can be something like this. And we know that it is solar gain factor through which we quantify this. Now, solar gain factor, if you look at it, this axis is total amount of the fraction of radiation. This range represents the reflection at any angle of incidence, say 80 degree, this is the reflectance R. This is transmitted, say 10 degree angle of incident, this is what is transmitted through it, and this is what is absorbed. So, part of the absorbed is actually transmitted back. So, in other words, theta at any point of time is given by this central line. Some will be in, some will be out. So, theta, the solar gain factor, is given by the central line. This is fully transmitted, absorbed light, part of it is transmitted. This is the absorbed light which goes out and reflected is thrown out. So, this is what is, So, if this is 1, total is 1, out of which this fraction is reflected, this fraction is directly transmitted, and this fraction is absorbed, part of it is then transmitted again, and this is a function of angle of incidence also. Obviously, you can understand, if it is coming parallel to the surface, nothing will be transmitted, everything will just pass by, right. So, that is why at 90 degree angle of incidence, because normal to the surface, the angle the rays makes with normal to the surface, that is actually your angle, incident angle. So, it depends upon incident angle as well. Therefore, you can understand that it will vary with time to time, because solar radiation will be incident at different angles at different time. So, it will be it will vary. However, we can take a single value as an approximation, or we can take theta varying with time if we can estimate them for the type of glass that we are using, right. So, that is what is the solar gain factor for glasses, right, solar gain factor for glasses, all right. So, we will go to the next one. Let us say this is coated clear glass, this is coated clear glass, this is what is transmitted, relatively less, as you can see. Absorption is similar, but large amount of it is reflected as well, I mean, we are talking of the total spectrum of solar radiation, right. So, that is how, all right, reflectance, transmittance, etc., etc. So, this is what related to glass. If this is your angle of incidence, and this is 0 to 1. So, highly absorbing glass will be somewhere here, which will absorb quite a bit, and this is reflected, this portion is reflected. So, absorption high, more absorption means this, more reflection obviously would mean this, and this is the transmittance. So, class can be chosen based on this sort of properties, Overall theta is what is, important, overall theta, that is important for us. So, choice of glass should be based on theta. All right, coming back to next thing is, but you got to find out how much will be the radiation, and you can see obviously you know how to calculate them out. In details we have seen that how to calculate them out at any point, at any location, on any surface, on a given day, at a given time, So, we have already seen that, but if you see the radiation pattern varying, that gives you a kind of good idea. So, for example, if you look at 1 degree south latitude, you find that if this is the time of the day, 6 to 18. Now, 1 degree south latitude. So, you find that maximum radiation is received in February, which is summer there. You can see similar one for 1 degree north. The only difference will be instead of July will go somewhere there, February will come down there. So, September is somewhere there. So, actually near equator, this is the kind of variations you will find, 1 degree south or 1 degree north. This is actually horizontal surfaces. Around 12 noon you find maximum radiation, 12 noon you find maximum radiation, right. And if you do for north surface, you get, this is during August and during June, but if you take 1 degree north, right, then this will become south surface, because north in southern hemisphere receives radiation, but north in northern hemisphere do not receive radiation, while south does, because banking of the sun is towards the south. So, this is 1 degree north. If it is north, then this will be south surface, and months will also change accordingly. So, you get, say for example, in south surfaces, winter months sun's altitude is less. So, south surface gets lot of radiation, but in summer month it will get less radiations, right. So, winter months it keeps on getting. So, here it is the summer months actually for northern southern hemisphere, north surface, these are actually winter months, sorry, these are winter months, they are corresponding ones in our case should be reverse ordered. So, this gives us some idea. I will summarize this a little bit more once we look at them, and this is on east and west surfaces. So, east and west surfaces, you find that during summer you get lot of radiation. This is east surface early in the morning till 12, and this west surface, right, and this is September, So, close to equator the tendency is to get radiation, this variation is order also, you can see this order of the order around 600 watt per meter square, this is the order. And if you go from this to, let us say, okay, and south in our case it will be north, I will come back to this again, but what I am trying to, if you compare this with the, let us say, some higher latitude 33 degrees south. So, in summer this peak is much higher in horizontal surface, just compare this, and we obviously know how to calculate this out, but we just compare this horizontal surface. So, summer months this was very much there, right, and 33 also this is high. So, horizontal surfaces always receive high radiation, horizontal surfaces in summer months, but winter you see it has gone down significantly. Even the time of sun, during the sunrise to sunset is now day is smaller. Here day is very large, summer months day is large, radiation received on horizontal surface is also large, as good as lower latitude close to equator, right. But winter day is small, while this was not the case in 1 degree, 1 degree, 1 degree, 1 degree, you know. So, day and night was more or less similar both in summer and winter, both summer and winter, right. And in winter also it gets sufficient radiation, there is of the order of around 400-500, but if you see this one, compare this with this one, compare with this one, you find that this is somewhat less than similar, although peak is, because it is horizontal surface, but daytime becomes less. So, total radiation received will be less. Well, this we understand anyway, because it is a function of latitude and declination, as we have seen earlier. If you see north surface in this case, which is equivalent to south surface in northern hemisphere, right. This is in winter months, this is in summer months. So, at higher latitude, south surfaces in northern hemisphere will receive low radiation in summer, while in southern hemisphere in north surface, in this is summer, this is summer, this is summer. If I put it equivalent January, you know, you put it equivalent, it would be somewhere in the July or something like that in our side, July or, you know, June, July around that time, and July scenario in northern hemisphere. So, it would receive much less radiation during summer months, south surface, and winter months it will receive maximum radiation, and duration also, duration obviously the day becomes smaller. So, but still is comparable. I mean, in summer months practically much less duration during which south, because in, you know, altitude angle of the sun is much lower at such latitude, because altitude is also a function of declination. Latitude, you remember that it is a function of declination, latitude, and of course our angle, yeah. So, that is on north surface, that is on north surface in 30 degrees south, and this is on east and west surfaces. Now, you can see again the summer months they get it, the east surface, it will just get reversed in our northern hemisphere, it will get on the east, you know, it will get slightly, July will become January and January will become July, otherwise it is all fine. So, this is the summer months, this is again January and this is July. So, in summer months in higher latitude, what you find that you get some radiation in the north surface also, and in northern hemisphere, and southern hemisphere south surface also gets some, I mean east surface, sorry, east and west get radiation in summer months, because the day is longer. So, you get early in the morning till 12 you get some radiation, and afternoon you get radiation. Horizontal gets radiation all the time, summer months it gets higher, winter months it gets less, because daytime becomes longer. So, this type of variation is important from the point of view of understanding next what we are going to discuss. So, this again you can see same 30 degrees south in you know south means it will only get some radiation, because sun rises somewhere beyond the east. In higher latitude day is long in summer. So, sun will rise not east, but somewhat beyond the east, actually a little bit depending upon where it is, which hemisphere it is. So, the day is longer than 12 hours. So, even the south surface in southern hemisphere receives some radiation in the morning, and you know in the evening also, afternoon just before sunset. Same case will be the north surfaces in northern hemisphere, because sun will rise a little bit north of the due east. So, and because day is longer, not 12 hours, slightly more. So, north surface will also get a little bit of radiation in the morning, early in the morning, and also in the afternoon. Now, what is important here is, because of this kind of variation, I can actually block the sun by providing something like overhangs. This is horizontal overhang over the window. So, this is the window or openings I can provide. So, since I can design them in such a manner, let us now talk of, I have given you explanation through southern hemisphere, but let us understand, because we are in northern hemisphere, it will be easier to understand the northern hemisphere scenario. In northern hemisphere, of course, in near equator 1 degree north or 10, 12 degree close to it actually, altitude angle of the sun may not be that low in winter as we have seen, but as you go away from it, altitude angle of the sun is quite lower, right. So, what you can do is you can provide this overhang such that summer sun is blocked, but it allows winter sun to go through, right, winter sun to go through. So, this will be for south facing windows in northern hemisphere or north facing windows in southern hemisphere, right. So, you can allow winter sun to come in, and these we call shading devices, this we call as shading devices. This is a horizontal shading device, this is a horizontal shading device. Now, I can have a vertical shading device also, I will come to this angle and all that later on. I can have, this is horizontal shading device, and this angle I will come to a little bit later on, and this is a this is horizontal shading, yeah, this is a vertical shading device. Now, when will you need vertical shading device? When the early in the morning or in the evening, because you see it should block from this side, it should block from this side, right, it should block from this side for south facing surfaces in northern hemisphere, or east facing surfaces you can put it on, east facing surface will receive, but altitude angle of the sun is lower. So, you will have to see that how you work it out. So, this is called vertical shading device, because it is vertical, while that is called horizontal shading device. You can have combinations, we will define this angle a little bit later on. You can have combinations, this is called egg crate shading device, that which looks like an egg crate. So, you will have combination of, like in hotel rooms you will see quite often, each room will have this kind of total I mean balconies and maybe openings of the kind such that the sun is blocked. So, it can be systematically done, these are called egg crate shading device, and you can have all kind of combination, you can have inclined shading device also. So, let us go back to them some, then how do you look at this a little bit more, define them through some angles, So, therefore, we can utilize these shading devices effectively to cut down the unwanted solar radiation during summer and allow them, because the length will govern this. So, we define certain angle, these angles are, first of all, you see I can draw a normal to the window or wall, normal to the window or wall, right, normal to the window or wall. And if this is the shading device, then maybe I have a diagram, let me see if I have a diagram, right. So, I can just drop it down from any point, this is normal to the window. So, this is nothing but height of the same height as the window height, right, this same height as the window height, and this angle, this is 90 degree, because I have dropped it down, and we define actually something called vertical shadow angle, and this is the vertical shadow angle, So, what is vertical shadow angle? It is the angle the tip of the shading device makes with the normal in horizontal plane. A line joining the tip of the shading device to the point on the window, interior point on the window, right, with the normal drawn from that normal to the window itself. So, this is what it is, this is what it is. So, I mean this will be same elsewhere if I draw. So, anywhere if I draw I will get the same one. So, at any point, you can take. So, basically this if this is your shading device in vertical plane, this angle I am talking of. I am talking of this angle. This is the, if I see from this direction, I see that this is the shading device, shade overhang. This is the overhang. This is the window height, and normal to the window is this. This angle in vertical plane, I call it vertical shadow angle. This is the characteristics of a horizontal shading. This is the characteristics of a horizontal shading. So, characteristics of a horizontal shading is vertical shadow angle, right. And how would I find it out? It is simply this distance, supposing I want to find out, this is say cos of this angle I want to find out. This is simply this height divided by, or tan is very simple, tan of this angle, let me say I want to find out, I define it as epsilon, I will just come to that. So, tan would be, tan of this angle would be equals to vertical shadow angle will be equals to this height, that is window height, height of the window divided by length of the shading device, horizontal, right. So, I can find out this one, right. Now, I got to relate it with the sun, I got to relate it with the sun, I got to relate it with the sun's position. Now, sun's position, if I want to relate it to, sun will be at some incline, it will not necessarily be normal to the window, it can be at some angle. Sun ray will be at some angle, I mean it may not be parallel to this, not necessarily. So, this is the sun ray and its projection onto the horizontal plane is this. Projection onto the horizontal plane is this, right. Projection onto the horizontal plane is this. So, this is the what is this angle then? What is this angle? Altitude angle of the sun. So, this is altitude angle of the sun, and therefore, this if I look at it, because I am dropping it down, it is normal, just normal to the horizontal plane. So, this is normal, this is also normal. So, I can get a relationship between the shadow angle and altitude angle, Now, this line must be parallel. If I join this line, now this line, because this is same, or in other words, not this I join. If I join this, my drawing may not be very good, because it should have been something like this, maybe may not be very good. So, if I join like this, right, this is dropped down from the top, I mean I have dropped one down from the top, and this I have dropped another down from the top, this is another down from the top, the angle, sun rays of course somewhat inclined. So, I can actually, this is the distance, or maybe I have a better diagram. Well, this is the line which will be parallel to, supposed to be parallel to this, it will be parallel to this, and this is normal, all this. So, this line is parallel to this is normal to that line. So, this is actually 90 degree, right, because this line, green line, is parallel to that black line, I mean parallel to this line, and it is normal to, this is normal to this one. So, this should be 90 degree. In other words, I can get relationship relating these two. How do I get it? Angle tan epsilon is HW by AB, that is what we have said already. Tan HW is the height of the window, and tan beta, altitude angle, will be again height of the window, HW by AC. So, this is HW, this red line is also HW. So, HW by AB and HW by AC. Now, I want to find out relationship between length, relationship between length. So, sec gamma. Now, what is this angle? Angle between normal to the sun ray in horizontal plane and angle between normal to sun ray in horizontal plane and normal to the wall solar azimuth. So, this is gamma is the wall solar azimuth. So, wall solar azimuth will be nothing but, because this is 90 degree, this is wall solar azimuth, and this this distance, I mean this distance I can't find out actually. AC by AB, AC by AB will be equals to, AC is the hypotenuse, AB is the this angle. So, cos angle will be AB by AC, sec will be AC by AB. Sec of secant of gamma will be equals to AC by AB, because this is the wall solar azimuth, this is the wall solar azimuth, this is 90 degree, this is normal to that one. So, AC is normal, AC is normal to line AB, AC is this is 90 degree, or angle ABC, ABC is 90 degree, angle ABC is 90 degree. So, AB by AC is cos AC by AB is, and gamma is the wall solar azimuth, wall solar azimuth, wall solar azimuth, right, wall solar azimuth. So, therefore, now I can relate this actually, I can relate this AC by AB. So, this I can relate actually, sec gamma will be equals to 10 epsilon by 10 beta. So, this is what I have done, sec gamma will be equals to height of the window. Anyway, this we have seen already, we have defined it already, HW is the height of the window, and 10 epsilon is equals to HW by LS 10 beta sec gamma. So, did I write it beta the same? Yes, 10 beta, right, sec gamma is equals to 10 epsilon. So, 10 epsilon can be written as HW by LS 10 beta sec gamma, a height of the window, length of the devices. So, length of the device can be related to length of the device, or 10 epsilon, or what we call vertical shadow angle, 10 of vertical shadow angle is related to altitude angle and wall solar azimuth at any point of time. So, you know the time at which you want to block it, you can actually you can actually find out, because at any time you will be able to find out first of all solar azimuth. So, wall solar azimuth, altitude angle of the sun. So, what is the LS required to block the sun at that point of time, you can find out, because 10 epsilon you can find.